Testing. Yes, thank you for coming. So this is a great follow-up to the last talk. So when we first started writing the abstract for AGU 2014, we were thinking about the role of climate change on the low precipitation over the past winter. As we started looking at the data, which is just coming in, and I will let you know why that is the case, we saw that actually the story is not quite complete if we only look at precipitation. Now, this has been a truly exceptional drought. Some numbers from NASA, for example, 11 trillion gallons of water needed to recover. But so we know, and then also the snowpack. Now it's been estimated that it was half of previous estimates. Now, NOAA they come out with a really nice report last week, and the main thing is natural variability was actually the cause for the precipitation, the lack of precipitation, the low precipitation last year, and due to the sea surface temperature. Also from La Nina, from North Pacific, and internal atmospheric variability. But they did leave the door open for what happens with the temperatures. Basically, it was said, well, we know the temperature is changing and it might have a role, and we will leave that for future studies. So that is where we jump in. So the impact of the temperature, as Sonia was talking about, we do have feedbacks between dryness and temperature, and certainly after 2 years of low rainfall, you might get pretty warm conditions. And in California this year, we had the warmest year ever on record, that is, through November, those are the latest figures. And so was it due to the dryness, or was it just a really warm year because of climate change? I say that it's a little bit of both. So now I want to jump to some observations. This is the maximum temperatures in the y-axis, the precipitation in the x-axis. Precipitation is in percent from the mean from August 2013 to July 2014. What we see is that 2013-2014 was the warmest and also one of the driest, but not the driest. There were 2 or 3 others that were drier and with relatively cooler temperatures, nowhere near as record-setting as this past year. So we want to know, why is this the case? Is this going to be the norm now? Is it not going to be the norm? Are humans affecting the climate? So now we jump into some of the attribution work that has been done. Peter presented some, and a couple of other speakers have talked about some of the attribution studies have been done that have been working on heat, which is actually, the signal is actually very strong for multiple areas of the world. Precipitation, not so much. It's because it's many, many variables removed from global warming, which is actual temperature of the planet. But recently, some new work has found that temperature and the precipitation indeed has changed. And one of the other things is just recently there was work done on the floods in the UK last year using the regional Superensemble modeling. And we actually were able to use some of the boundary conditions from those simulations to drive our simulations. And we will examine the drought through February of last year, and the reason for that is the simulations that my collaborators at Oxford did went only through February. They did not have the full sea surface temperatures and sea ice information for the rest of the year, so we will keep our analysis through this month, through the month of February. So we use the regional model Superensemble through climateprediction.net framework. This is our domain. Again, I'm limiting it to where most of the drought was through February of 2013. We're doing full forcing runs with Hadley and Ostia, SST, sea ice. The natural runs with the historical natural SSTs set at 1900 level CO2 for these 4 models. And so now we have a great ensemble of opportunity to work with. So first we started looking at decadal changes. And we see here in the green 1960s. In this plot, this is a return period plot with precipitation on the y-axis. We have the green 60s. In the brown, the 2000s, we see that the change in the return period here, and also the fact that it's much, much drier for the 2000s. Now, if I were to just end it right now, you would say, wait a second, what about natural variability? What was happening in the 60s that was different in the 2000s? Weaker La Niñas, for example. So, to address that, we do for the same months, DJF for the 2000s, full forcings and natural. We see a slight signal for the natural runs where it's wetter than the full forcings, but it's not really quite surpassing the margin of error, the error bars here in these hatchings. And so we tried 2013, 2014, and we see that there really is no appreciable difference between the two. But that's not the whole story. If we're talking about other variables that are important for the California drought, for example, we have snow. Now, the snow water equivalent on February 25th, 2014, shows that the natural runs are appreciably higher than the full forcings. We're talking about a third more snow in the natural. It's also outside of the error bounds here, and I just want to mention also the fact that the changes in the error bars are the number relate to the number of model runs that we have for specific simulations. And so, unfortunately, we couldn't get all of those model runs because these model runs are running on people's computers, people's private computers, and so not everybody has 8 processors. Sometimes they just have 2. So it runs slower, so we don't get everything all at once. And so one of the other things that could affect the snow is the temperature. And we look at the temperature for the same region, and what we find is that the natural runs are much cooler. Or I want to say the opposite. The full forcings is about 1 degree higher for most return periods, except for near the end, the more extremes. And certainly that could have an impact. But these are the temperatures during the winter. If we are to look at the summer, June, July, August temperatures, first let's look at the observations here on the left. These are from NCDC based on 47 stations relative to the 1901-1960 average. We find that for this region of California, it's about half of a degree warmer than the reference period for the summer. So we want to look at what would affect the evaporation during the summer months. For example, we look at a variable like days over 35 degrees in a month, and it's here for the 100-year return period, for example, it's about 1.5 days more per month that reach this temperature. Also, for the average monthly maximum, ends up being about 0.5 degree for most of the return periods here, where the 2000s were warmer than the 1960s. But again, this is just a comparison between decades. So if we want to look at full forcings versus naturals for the same decade for the 2000s. Unfortunately, we couldn't get all of the model runs in, like I was saying, because a lot of the model runs were on queue for people's computers. But we did get enough for these 3 CMIP5 models. And what we find is that full forcings is appreciably warmer, or sometimes 3 to 5 times as likely to have a 100-year event. What we find for the summer months. So what the results suggest is that we basically agree with Dr. Herling and many of the other studies here that low precipitation pattern for the winter of this past year was part of natural variability. Also, unlike the total precipitation, low snow and the warm winter temperatures and the summer temperatures, are partly attributable to global warming and are 3 times as likely in a full forcings world, that is the world that we live in. But what this really means is that the risk of seeing a drought like the one we saw might be larger today if it hadn't been for the heat trapping emissions due to industrial activities. So that's what I have for now. We are working on completing the 2014 simulation so that we can look at the actual summer of 2014 and see just how much warmer it was and other variables. And just like to thank a couple of people. I'll take some questions.
Any questions? Go ahead.
On your 2 conclusions, the first one you say the drought is probably due to natural variability, and then your last conclusion says that man-induced climate change is going to increase the chances of drought. Where does that last conclusion come from?
Well, what I meant by, thank you for asking the question. So you're saying that after talking about all the different variables, at the end I say, well, the increase in the drought is due to climate change. I meant to say, like, so the variables like temperature that could create a feedback mechanism, we are changing the baseline of the temperature. And so the temperatures will be warmer and there will be more evaporation. And so the type of drought that we saw might be more likely to occur in the future.